Okay, now if we take a region in a plane, and here we have a rectangular region in the plane. The rectangle has a height of r, so the height is r, and a width of w. So you see the width here is w. So we take this rectangle, which is a region in the plane, and revolve it around or revolve it about a line. So the line that we're going to revolve it about is this line right here, and that line is going to be called the axis of revolution. All right, so we're revolving this region, which is a rectangle, about a line, which is called the axis of revolution, and it's going to result in a solid object. And that solid is going to be called a solid of revolution. For obvious reasons, it's a solid that is created by revolving a region about some line. And the line, of course, we said already was the axis of revolution. The simplest such solid is a right circular cylinder or disk, which is formed by revolving a rectangle about an axis adjacent to one side of the rectangle. So here you have the axis of symmetry, and notice it's adjacent or right up against one side of the rectangle, basically this lower side that's the same length as this upper side. So we have right here, this disk right here is a solid of revolution, and this is the simplest solid of revolution. All right, so the volume of this disk is the area of this circle here, which is pi times r squared, because remember, this distance right here is r, and that happens to be the radius of the circle on this face of the disk, multiplied by the width of the disk. And the width of the disk is just w. And w corresponds to this same w over here, because as you can see, the rectangle the rectangle is still present inside of the disk here. So there we have the rectangle with w for the uh, distance here and r for this distance, which would be the radius. Now, a few common a few common solids of revolution. We have the axle of a car here. The axle of a car, if you look at it, is a solid of revolution. This part here is just a disk, and this is just a wider disk. So this thing could be modeled by using a method where we could sum up a bunch of small disks to get the entire volume as an approximation. A funnel is also a solid of revolution. Here's the axis of revolution here. Here the axis of revolution is horizontal for the axle. The axis of revolution is the x-axis, or some line parallel to the x-axis. For the funnel, the axis of revolution is the y-axis, or a vertical axis, and or some line parallel to the y-axis. A pill, here we have a pill. A pill is also a solid of revolution. A bottle is a solid of revolution. And a piston for a car is a solid of revolution. So all of these things can be modeled as solids of revolution. And what we're going to be doing is we're going to be finding the volumes of such solids, which might be something beneficial to know. Okay, so to calculate the volume, the region that we are going to revolve about the axis of revolution is going to be called our representative rectangle. So we have a representative rectangle that's going to be the representative of all the regions that we are going to revolve about our axis of symmetry. So we want this region to represent the entire plane region. So this entire plane region is going to be revolved, but we're going to use a single rectangle since we want to create simple disks. We're going to use a single rectangle to represent this entire blue plane region that we are going to revolve about the axis of symmetry. Now, we're going to look at the height of the rectangle and the width of the rectangle. So we're looking at length being r and width being w, but in this case, we're looking on the x-axis, so the width is actually going to be a difference of two x values that are between x equals a and x equals b. So we're looking at this function, the r of x, which gives us the heights of all the rectangles, which is really the radius of our disk. And the x values are going to be between a and b, so we're looking at this closed interval from a to b, and on this interval we have defined some function r of x. And r of x is basically this function right here that defines our plane region. So that's the r of x, and it actually gives us the height of the representative rectangle. Now the width of the representative rectangle is given by delta x, or if I have this x value here and this x value here, delta x, let's call this one x2, let's call this one x1. Delta x would just be that difference. Delta x would be x2 minus x1. And this representative rectangle would have an area that would be the r of x, which is the height of the rectangle, times delta x, which is the width of the rectangle. So we have these two players. We have the r of x, which is the height, and delta x, which is the uh, width of the rectangle. Now what we're going to do is we're going to take this entire blue region and we're going to revolve it about this axis. So we're going to spin it around and it creates this shape right here. Um, Kind of a conical shape, but there's a curve there. You see the curve r of x is present there, and this is our representative this is our representative rectangle actually. Representative rectangle would be this one here, but it creates a disk, and the disk you can see inside here. Now what we're going to do is we're going to take all these disks that we get by changing where we are along the x-axis, and all those disks will give us an approximation of the volume of this solid of revolution. So we have the axis of revolution, the representative disk. If we take all the representative disks and take all their volumes and add them up, we'll get an approximation, and this is the n disk approximation. This actually has 1, 2, 3, 4, 5, 6 disks. But we could make n, as many disks as we want. Now this approximation becomes better and better as delta x goes to 0. Remember, delta x is how far, or the width of the rectangle. So as you get the width of these rectangles to be smaller and smaller, you get more and more disks. So as delta x goes to 0, n actually goes to infinity. As the width of the disk gets smaller and smaller, you get more and more disks. So you can define the volume of the solid to be this. Well, the limit as the width of each disk goes to 0 of pi times the radius squared, which is the volume of each disk, multiplied by delta x. Well, actually, sorry, this is the area. Pi times r squared would be the area, and you multiply it by delta x and you get the volume. So it's the area of the circle, which is pi r squared, times the volume, or times the width, which is delta x, to give you the volume. And this sum just means we're adding all of them up as the limit, uh, as delta x approaches 0. That's actually the definition of this integral. So this integral will actually be all we need to find the volume of a solid of revolution. Once we can identify the radius of each disk, and delta x will represent the width of each disk, the sum just means to add them all up as delta x goes to 0 and multiply it by pi. So this will be the volume, and that leads us to the disk method. All right, so to find the volume of a solid of revolution with the disk method, use one of the following as shown in the figure. So we have a figure below here, and which one of these two equations we use to find the volume all depends on whether our axis of revolution is horizontal, meaning parallel to the x-axis, or vertical, or parallel to the y-axis. If we have a horizontal axis of revolution, we have to get the height of each disk, or the radius of each disk. We have to get a function in terms of x and integrate with respect to x. But if we have a vertical axis of revolution, then the height of each disk, as you see here, the radius of each disk is actually going to be a function of y, and we're going to integrate with respect to dy. So here we have a horizontal axis of revolution. Here we have everything. The function is here. This is the function r of x. This function looks like a circle or a quadrant of a circle, but that would be the r of x, this function right here. So we have the function the r of x, and we're going to make a representative rectangle underneath r of x, and that representative rectangle has to be perpendicular to the axis of revolution. So here's the axis of revolution. Here's the x-axis, it looks like, or some axis parallel to the x-axis, a horizontal axis of revolution. And our representative rectangle has to be perpendicular to that. The radius, the radius of the disk has to be perpendicular to the axis of revolution. Delta x is the width of the disk. And over here, it's exactly the opposite. Once again, here's our axis of revolution. So we need the radius of each of these disks to be perpendicular to the axis of revolution. So here is the representative rectangle that's going to create our disk. And notice the radius here is, when we revolve this thing, going to be perpendicular to the axis of revolution. So depending on whether we have a horizontal or vertical axis of revolution, we're going to either use this formula or this formula. All right, so now the disk method can be extended, because if you take a disk and you cut a hole out of the middle of the disk, you will get what's called a washer. So an extension of the disk method is called the washer method. Now, the disk method can be extended to cover solids of revolution with holes by replacing the representative disk with a representative washer. So the representative disk is going to be replaced with a representative washer. And the only difference is, instead of the region in the plane extending all the way to the axis of revolution, there is now going to be a gap between the plane region and the axis of revolution, and that gap is going to create a hole in the middle of our disk, and that hole is going to have a little radius, that hole is going to have its own radius, and we're going to name that radius little r. So now we have big R, which is the radius of the disk, and then we have little r, which is the radius of the hole that we take out of the disk to form the washer. So here we have a washer, and W is still the same. W is still the width of the washer. Um, but now we have big R, which is the same big R that we saw before, the radius of the disk itself. And the hole that we want to take out of the disk has a radius of little r. So we create a washer. And here is the volume of the washer. Well, they actually simplified this a little bit. What it was pi times big R squared minus pi times little r squared. And uh, actually, that would be only if I was looking at the areas of the circles. So it's actually pi times big R squared times W. This would be the exact same thing as the volume of the disk. And we're subtracting out of that a smaller disk. We're subtracting from that the volume of a smaller disk, and the volume of that smaller disk is pi times little r squared times W. So basically what they've done is they've just taken the outer disk and subtracted the inner disk's volume from it. So we're taking the volume of the outer disk and subtracting from it the volume of the inner disk. And we create a washer, and they just simplified that expression to get this one. All right, so what we want to do now is we want to look at how this can be made into a calculus formula. So to see this concept can be used to find the volume of a solid of revolution, consider the region bounded by an outer radius of big Rx, which is the radius of the outer disk, and inner radius little rx, which is the radius of the inner disk that we're going to subtract the volume of the we're going to subtract the volume of the inner disk from the volume of the outer disk, as shown in the figure. So the figure is down below here. right? If the region is revolved about its axis of revolution, the volume of the resulting solid is given by this. This is the washer method. So we have this, and what it is, basically, we have the little radius, which would be this curve function right here, this curve function, that would be the inner radius because we're going to revolve around this axis. So the plane region is this blue region that we're going to revolve around this axis. So we're looking at a representative rectangle. A representative rectangle is going to have its radius, or the radius of the disk that it's going to create, be perpendicular to this axis of revolution. So we're going to draw our representative rectangle in this way to represent this entire blue region here. So you see, because this is the axis of revolution, there's an inner radius that stops here, which is this bottom function here, which looks like some kind of quadratic function or some kind of curve function. And then the top function, which is the outer radius, is determined by this function right here, which seems to me to be a linear function. So we have an inner radius, Rx, and an outer radius, big Rx, capital Rx, to represent this plane region between, on the interval of the x-axis between A and B. When we revolve, we get this shape right here. It's kind of a cone. There's kind of a bevel on the inside because of the inside function being quadratic in nature. But this is how we are going to find the volume of a region using the washer method. That is the washer method.